today's session, I will try a different approach, that is, a graphical approach to approach these problems. Oh, 16 people. That's more than I expected. Okay. Um, uh, this might provide an intuition towards what um, is being taught in class, but might not be in that detail. But I think you might enjoy it. Yeah, so what is multivariable calculus? We have heard of single variable calculus when which deals with functions which has single variables. Um, but these variables are with respect to functions. So what are generally what do generally functions do? They take in an input and spits out an output. Uh, it goes into some magic box and some single value output comes out. So this is what most of the functions do, be it a parabola, be it a cubic equation. Most of the functions have a single valued output, but we have unknowingly explored other functions as well, um, which um, which take in different number of inputs and spits out different numbers of outputs. For example, you might be familiar with the projectile motion when we throw a ball. It is when we how do you represent that in terms of t? Suppose for a projectile motion to represent the um, what do you say, the path of the projectile, we use the parametric form in terms of t, which means we represent the x coordinates with v naught um, cos theta into t, while we represent the uh, y coordinate with what do you represent? Uh,
Sine
wait,
theta.
yeah, sine theta, but wait, I forgot. Um, S is equal to ut minus half at square. So v naught sine theta minus half gt square. So this is the parametric form. So what does this do? It takes in one input, which is the time, and spits out a vector, which gives the vector means it spits out the position of that point, which we can see as a vector x comma y. This is nothing but x comma y written as x y. But the problem with this is when we do this, it loses a lot of information. For example, it surely gives out the path in which it goes, but we don't know at which time, which path, which point it is at this path. So that is one um, con of using a parametric form. Um, the other example that we have seen is in rotational motion. V is equal to omega cross r, where the inputs are two vectors and what we are getting out is another vector. Even gravitational field and gravitational potential is another example of multivariable functions that we will see in detail later when we go into function potential. It's very relatable. And yes, so these functions give us an idea that functions need not just have one input or one output. And from this idea starts our journey with multivariable functions, where you can have n number of inputs and n number of outputs. At many times, this need not be able to be visualizable in a graphical representation, which means we can put, even if it is a 3D, we can put it in a graph only if it has three parameters, at least two inputs and one output, or one input and two outputs, or maximum 4. We can use colors to represent some more information. But generally speaking, we can have n number of inputs and n number of outputs. Yeah, so let's come to the topic where I I think will give you an intuition about thinking about these multivariable functions. So what do you think this picture here represents? Is it a desert? Desert? No, it is just the graph of sin x cos y. One way of like relating with multivariable graphs is by keeping one variable constant and treating it as a single variable function, which we are already familiar with. So we will try doing it here. I think it'll take some time to load. I'm not sure. We will slice the sin x cos y graph and see how it looks at different fixed points of each variable. Oh no, this. Yeah. So here we have the same graph that we viewed earlier, which is the sin x cos y graph. Now, let's take one value constant. Let's take maybe y to be 0. Then the whole equation will get converted to, because if y is equal to 0, then cos y is equal to 1. So it will become z is equal to sin x. So let's see if that's what we get here. This is the x-axis. So when I keep y to be 0, you can check it out. What you get is a sine function when you view from it's a sine function, exactly a sine function, which you can graph it as z is equal to sin x. Now, if after you have seen this, can you guess what will happen if we fix x to be 0? This is the x-axis. If we fix x to be 0 and slice it at the y, yeah, slice it slice it exactly at the y-axis. So what do you think we will get? Any answers? X is 0. Arjit, what do you think?
Can you repeat on?
If x is 0, like when we put y is equal to 0 and sliced it at the wait, I'll mark the coordinates just in case for you to easily see it. Yep. So this is the x-axis, the red is the x-axis, and the green is the y-axis. So when I the y as 0 and slice it at the x-axis, I get a sine wave, which is what we expected. Because see, if y is equal to 0, then cos y is equal to 1. So what remains is z is equal to sine y, which is what we get, a single variable function. But now, if I fix the x value, what do you think we'll get? As 0.
I think we'll get a fixed point.
Why?
Sine 0 is 0, right? So the function becomes 0.
Yeah, so it'll become z is equal to 0, which
It will be.
is a straight line. Like it is 0, like we expected. The entire for the entire region, z will be equal to 0. There's no point where z is not equal. I mean, z takes any other value. Yeah, so that is one way of analyzing function. Yeah, maybe we can go a little more ahead. Let's say let's say y is equal to No, wait. Let's say x is equal to pi by 2. What do you get now?
Graph.
Yep, because yes, correct. Because sine pi by 2 is 1, and what remains is z is equal to cos y. And we'll see that here. Pi by 2 will be around 3.14 divided by 2, right? In radians. So it'll be around here. Yes. And like we predicted, we're getting a cos graph. So, you can even take, oh, did I invert it or something? Yeah, you can even assume a multivariable graph to be a stack of these single variable graphs stacked on top of each other. So that is one way of slicing graphs and visualizing and relating with it. Basically, I'm doing this so that you will have a better intuition while seeing a multivariable graph. So it doesn't feel like deserts or any other weird shapes, just as any shape. Yeah. And so there are many visualizations to see multivariable functions as. One of them is graphs, and like we discussed, it has a little limitation because it can represent only a maximum of 4 parameters. If we include color. If we take 3 input, if you want to represent maybe 3 inputs and 1 output, okay, we can do it because of the color thing. But if you want 4 inputs and 1 output, we can't. Because we are limited by the dimensions. One another way of seeing multivariable visualize multivariable functions is through contour maps. Contour maps is by basically like let's take some random function. No, not this. Duplicate. Yeah, let's take maybe function called x square plus y square, which looks like a cup. What do you think the contour plot of this would be? So I will explain what a contour plot is. A contour plot is basically level surfaces. Planes where the entire z is the same value. So maybe at 2. For this function, at what and all values of x and y is z equal to 2. So all those values will be basically contour plot is they're compressing all those values in a 2D plane. So if we search for the contour plot of this, I don't think I was able to explain it properly. But still, I think if you see the graph, it'll give you an idea. Wait, I'll just search it. Contour plot map of x square plus y square. Yes. See, this is how the contour map of this graph looks like. You might have got an idea why it looks like that, because we are taking the level planes of this graph and then compressing it to a 2D plane at different intervals. Is it mentioned? Yeah. So at 1, where are all the, yeah, so 1, let's take 1 for example. At z is equal to 1, at z is equal to 1, at if we slice at z is equal to 1, we'll get a circle. I don't think I have to do it. It is easily imaginable. If I slice at z is equal to 1, you'll get a circle. The same with z is equal to 2, z is equal to 3. All those slices, we are compressing it to a 2D plane. So I guess that was enough. Was that enough? Yeah. Yeah, so what is the con here? It shows only the input space, like we saw in the map here. It shows only the input. Here we have to like externally manually write the outputs here. So that is one negative side. We usually use it when we have a 2D input and 1D output. Basically, for the reasons we use multivariable graph. Normal graph. Another way of representing multivariable functions is what we discussed earlier. For maybe the projectile motion, we represented the path of the projectile using the parameter t. There what we had one input and two outputs, which we represented as a vector or a point. When output has more dimensions than input. Yeah, and like we parametrically represented a 2D path there, we can parametrically represent a 3D curve also. So that I'm not going to that, but yeah, we can represent. And another way of looking at multivariables is vector fields, which we had done in class. So let's take a simple vector field like you might remember doing this in class, I'm not sure. Y and X. Basically, this is it'll take. I'll try. What it means is if we have an input X comma Y, two inputs, it will give a vector, some vector. We can define this vector. This is the function. This is some function that does this. We can define this in whichever way we want. We can define it as maybe it'll give the same function out, which means if x, y is the input, x comma y is the input, it'll give x comma y as the output. Let's see how that looks like. See, it's an identity vector. Basically, if you look at every point, it'll show the basically it's an identity vector. And how are we plotting this? We did this in class, but I think ma'am went wrong somewhere. So you might have a little bit what I'm doing might feel a little different. That's why I'm doing it, to be honest. If you check the recordings, Abhinav pointed out to me. Is he here? Abhinav? Nope. Yeah. So let's say this is an identity function. Basically what this is, let's try if we can do it manually. Let's take 1 comma 1. What will it output? 1 comma 1. Sorry. 1 comma 1, which is basically I cap plus j cap. How will it look like? If you simply take the vector I cap plus j cap, it will be a vector like this with 45 degrees inclined to both x and both I and j vector with a magnitude of √2. But when we are plotting it, how we are doing it is we are placing the tail of this vector in the input. Here the input is 1 comma 1. So and then we are replacing and basically we are putting this vector I plus j, which we got as an output, from the tail 1 comma 1. Basically we do this for all vectors. If it's 1 comma 2, it'll be I plus 2j, which will be around like this. And I plus 3j. I think I'm doing it right. Oh wait. I plus 2j will be like this and like this, if you look at it. Yeah, okay, wait, am I wrong? I plus 2. Yeah, I might be wrong, but this is how you get it. Am I wrong? 1 comma 2, 2 comma 1. So here, Yeah, it'll look somewhat like this. If we try inverting the values, let's take. I know this is a little boring, but okay, this time let's do it properly. 1, 1. If 1, 1 is the input, what we get is some 1, 1 output. Basically a vector looking like this. If 0, 1 is the input, which is here, what we get is a vector that looks like 1 plus yeah, so it'll be like this, I guess. 0, 1. Yeah, if it's 0, 1, it'll be 1, 0 will be the output, I and j. So yeah, so this will be like this. So this keeps on going, and if I plot it here, yeah, you get somewhat like this. Yeah, see, at exactly here, it's at it pointing in the right direction, just like how we predicted. And even this side, it goes like this. So this is manually plotting it, but I think you got the method. I think I messed up the first example, but yeah, it's because I'm nervous. Sorry. Yeah, so those we saw different ways of thinking about 3D graphs. Is there any doubts? If I'm messing up the first example, I feel bad.
We got it. It's good.
Yeah. Okay. So before going to partial derivatives, what is a derivative? In single variable for single variable functions, like maybe x square and x cube, how do you define a derivative? How does an x square graph look like? Like this, and this is y, the output, and this is x, the input. So we define the derivative as dy by dx, which essentially is a slope of the graph at any point x. At any point x. The same with a cubic function, dy by dx. If you find it, you'll get 3x squared. For the quadratic equation, will be 2x, which means at any point x, the slope corresponding to that point will be 2x. So this is how we see derivatives in as for single. If I have the formal definition of a derivative, it has something to do with it will have something to do with limits. Wait, I don't want to mess up that too. Wait, I'll try writing it on my own. Limit h tends to 0 while f of x plus h minus, please tell if I'm going wrong somewhere, by f of x, oh wait, sorry, f of x by h. Is this right? This is the formal definition of a limit of dy by dx. That's right, no? Can anyone confirm? Abhijeet.
I think yes. Wait.
Okay. We'll try to relate this. Okay, tell me if it is wrong at any time. Interrupt me. I mean, I think it's correct. Okay, so we'll try to relate these graphs with 3D graphs. This again is to give you an intuition so that the next time we look at the notes, it won't feel weird. Yeah, so we know that this is a cup. Maybe to understand the example better, we will change y square to y cube. Can we? It will look somewhat like this. Oh wait, I'll do it here since I already have the. Oh, this. Sorry for the time. Yeah. Let's basically cancel this function and put x square plus y cube. Yep. Yeah. Does anyone mind telling me what will be the function if I slice it at y is equal to 0?
It'll be x square, right?
Yep, it'll be a parabola, and it is a parabola like we predicted. Yeah, so what do we mean by a partial derivative in terms of a 3D graph is it has the same definition as the 2D graph, but here we are fixing the one of the variables. Like for example, we are differentiating it with respect to x. We are fixing the y at some point. It can be this, it can be this, it can be this, it can be this. At any point we are fixing it. I'm just taking 0 because it's easier to visualize, easier to see. But at any point, what is the slope of this graph? That is what a partial derivative means. And now what is a partial derivative with respect to y? We saw the partial derivative with respect to x. If you find the slope of that parabola that at any point x, basically, okay, wait, we have the function x square plus y cube. This is different. Yeah. So if we partially differentiate it with respect to x, we get 2x, because it doesn't matter what y is. We are considering it to be constant, and if we are partially differentiating it with respect to y, what do we get is 3y squared. Any guesses on what the graph will be if I slice it at y is at x is equal to 0? Basically, I'm fixing it at x. I'm fixing x. How will the graph be? It'll be a cubic polynomial. Yes, it'll be looking like x cube. And finding the derivative of this using conventional derivative terms is what we call partial derivative of f of x, f of x comma y, a of x comma y here. So this is what partial derivative means. Basically fixing one variable and finding the conventional derivative with respect to the other variable. For example, here fixing y and finding derivative with respect to x, or fixing x and finding derivative with respect to y. So that is partial derivatives. I think that was enough. Yeah, so mixed derivative theorem is I don't find any graphical logical reason, but there is a logical reason behind why this is true. It basically says that if you're different, okay, wait, we'll see it as it goes. We will try to, how can we differentiate this term? We can differentiate it with respect to x, or we can differentiate it with respect to y. Those are the two possibilities. We will try differentiating with respect to x. It will become 3x squared y to the power 4. And if we differentiate it with respect to y, it will be 4y cube x cube. Tell me if I go wrong somewhere, okay? And if we again differentiate with respect to, and again, what are the possibilities here? We can differentiate, either differentiate it with respect to x, or we can differentiate it with respect to y. If we differentiate it with respect to x, we get 6x y to the power 4. And if we differentiate it with respect to y, sorry, xx, because we are differentiating it twice. And here, if we differentiate with respect to y again, we get 12x square y cube. This also has two options, like we saw before. Differentiating with respect to x again, you'll find that it is also 12x square y cube. Did you notice it? These both are same. And if we differentiate with respect to y again, we get 12y square x cube. I think this kind of gave practice also, and we saw that it is the same. Basically, what it's saying is fxy is same as fyz. There is one logical way of thinking about it, but I don't know if I'll be able to tell it properly because I'm not a very good speaker. Okay, but I'll try. So, yeah, so for f, so this what this basically means is d square f by dx dy is equal to d square f by dy dx. Fine. So what is the left hand side doing? It is it's first differentiating it with respect to x. It is fixing y as a constant and finding the slope. Then after that, it fixes x as a constant and finds a slope. The right side also does the same way, but ulta. It first fixes x as a constant. Yeah, it first fixes x as a constant and then fixes y as a constant. So it basically finds the same thing, the same double partial derivative. I don't know if that made sense, but even that is one way I think about it, but it might not have a proper reason. Okay, so coming to gradients. Gradients has a very interesting way to look at it. Basically, the definition of a gradient is by combining the definition of a partial derivative. We represent it as del for the scalar field f, which is equal to del f partial derivative of f with respect to x. Basically what gradient gives is a direction. Basically a direction. What it gives is just a direction. J cap dou f by dou z. This is the formal definition of a gradient. So how do we view it? What does this mean? Let's take an example. Taking an example always helps. Let's take the classic example of x square plus y square. What does this give in terms of this? Basically okay, I'll tell it beforehand. Basically what a gradient tells us is the direction of the steepest ascent or descent. Okay, wait. Yeah, so let have here we get 2x I cap plus 2y j cap, right? So we'll see it in terms of the graph. Yeah, you see the graph. What does it mean? I said a definition of a gradient. Direction, this is important. direction of steepest ascent or descent. Ascent, descent. So if I am at this point, maybe if I'm at 1, 1, let's say 1, 1 is around here. Able to see, cancel. Yeah, so if I'm at this point, if I'm standing there, in which direction should I climb so that I can climb up the fastest? That is the question that I'm asking. If I am at 1, 1, corresponding to this axis, if I'm in that part of the curve, in which direction should I climb so that I reach up the fastest? In where can I climb the fastest? So if we put values in here, if we put the value in the gradient formula, which direction do I get? Basically I get 1, 1, right? 2 I cap plus 2 j cap. If you see, the direction is just I plus j. If you're just looking at the direction, what the magnitude gives is what is the magnitude here? 2 to 4 to root of 8. That is the magnitude. Basically that tells us how much we are climbing. That we will ignore for now. Basically, let's see the direction. This gradient basically gives us the information that if we go in this direction, in the I plus j direction, we can climb up the highest. I don't know if, okay, wait, I'll use my cursor. If we go in this direction, we're able to see, basically in this, if we travel in that x is equal to a y line, we can climb up the highest. That is basically what a gradient gives information of. Yeah, so that is a simple definition of gradient. There can be in this equation of f, even z term can be included, but the problem is, like I said before, we cannot represent it in terms of graph, but the idea is same. Direction of steep and ascent or descent. What ma'am gave us is, wait, let me check what she gave us. Okay, never mind. I don't know if I wrote it. Gradient is a multidimensional rate of change of a particular function. Okay, never mind, sorry. Yeah, so function potential coming. Yeah, any doubts in gradient? I think that was a beautiful example. I liked it, the way I explained. I don't know. Did you get gradient? Was I able to explain it better?
Yeah, it's clear now.
Okay, wait.
Yeah.
Before that, let me get some feedback. Vote in. Yes, so yeah, you might have heard these terms somewhere. These are all terms we discussed in physics, maybe in 12th grade or 11th grade. We will see how this relates to multivariable calculus here. So what is the potential? Let's talk about all these in terms of gravitational example. Basically, what we're talking about here is a gravitational potential energy, gravitational potential, gravitational field. Yeah, so you might have heard of this formula. V is equal to what? Infinity minus x. I'm not sure if you have seen this. So basically what it says is V, yeah, okay, basically potential energy, if you look at the formal definition, is the work done to bring 1 kg of 1 unit, 1 kg mass from infinity to x. So what is the definition of potential? It is potential in general is the capacity of something to do work. So that is the definition. You can even see potential energy as potential energy at infinity minus potential energy at x, or it might be the inverse, I'm not sure. Yeah, so basically that's what it means. Another way of looking at potential energy, yeah, so we discussed gradient, right? If this gradient equals, if this gradient outputs a vector, we know that that's what we saw in the previous example of gradients. It is giving out a direction, some direction. If this gradient again gives out a direction, and that direction can be related to a field, then we call f as a potential function. The same thing happens here. If you just do the inverse of this, dou v by dou x is equal to E, where E is the gravitational field at that region, and V is the potential. You can relate it, where F is V and the field is the gravitational field. This might not be that clear. I might not have explained it properly, but I guess we can continue with this. Maybe the analogy was proper. Analogy is correct, but yeah. So we talked about derivatives. Let's see what is, derivative with respect to x and y. But it is true that we can find derivative for any arbitrary direction, not just with respect to x and y. So what I'm basically mean by that, yeah, so the formal definition of a directional derivative is del f, which is a gradient, the direction of steepest ascent, into the projection of del f in the direction which we are looking at. This is the unit vector of the direction we are looking at. Yeah, we will try to. Is there a better way I can put it? I don't know. Okay, wait, I have an idea. Yeah, so let's say del f for something is okay, wait, let's take the general form of del f for x and y. Del f by del x I cap, del f by sorry, not del f, partial derivative of x f by x, partial derivative of dou f by dou x dou y j cap. So this is the del f. Let's ignore k cap for now. And okay, so now using this del f, I want to find the directional derivative with respect to x. Again, we know what it is, but I want to find it again. Now, what is the direction of x? Okay, wait, I'll draw it in 3D. This is x, this is y, this is z. What is the direction of x? I cap, right? Basically 1, 0. If I dot, okay, how can I write 1, 0 properly? Basically I cap. So if I dot this with this, what do I get? The directional derivative with respect to x is basically dou f by dou x, which is as expected, which is a common sense, but I did it to make you understand that this is valid. This is not wrong. So we will try to solve an example. Maybe that will give some clarity. Yeah. So using the example of a directional derivative, which is del f dot b cap. What do we get? Del f is dou f by dou x I cap plus dou f by dou y j cap. Does anyone wants to give me an answer? I'll do it. 2xy I cap plus x square j j cap. This is del f. And sorry, this is x comma y, by the way. It's a function in terms of two variables. Yeah, so we want to find the directional derivative with respect to the b vector. How can we do that? Basically, this is like saying I'll try to connect it with the slicing analogy, slicing and finding the derivative. To find the derivative with respect to x, we sliced it at y is equal to 0. Remember? Now to find the derivative with respect to this direction, we slice it at that particular 1 comma 1. Basically, what does it represent? This. Okay, wait. I forgot that we are in 3D. Yeah, 1 comma 1 basically represents this direction. So I put the plane here and slice it with respect to this. Slice it exactly at this point. I hope I got it. Yeah, and then find the slope. Yeah, and dot this del f with I plus j divide the unit vector, so divided by root 2. Fine. What do you get? You get root 2xy plus root x square by root 2. We'll try to look at this is basically del f by del in the direction of b. How do you represent it? I don't know. Yeah, okay, yeah, I remember. F by b. This is how we represent it. What this tells us is the slope when we slice it in the direction 1 comma 1. We'll try to look at it. Yeah, is this the same function? Oh, it's x square. Okay, I'll change it. So if x square y this is, and if I cut it with respect to 1, and are you able to see it? This is 1 comma 1 direction. The plane is currently in the I plus j direction. I cut the graph at that point. What do I get? I get this seemingly cubic equation. And if I plug in the values for x and y at any point of this graph, okay, it's not a cubic equation because it is different. If I, am I right? Yeah, it is right. So if I plug in the values of x and y at any for this directional derivative, I get the slope of this segment of the 3D function. So that is what directional derivatives mean in terms of graphs. And if anyone found something wrong with whatever I thought, please tell me. How many are there? Yeah, 14 still there. Nice. Okay, I'm not voting. Yes, so that kind of ends what I have planned for today. You can see this thank you slide, which I made and which I took from the internet as a graph. Does anyone have? Did anyone find any mistakes with whatever I told? Or any doubts, Abhijeet?
No, for my side, it's clear.
Okay, wait. Before you all go, I have another this thing also poll. Answer that as well. And in the meantime, like, okay, we will give one more try to do the vector field. for x comma y. I think I messed up before. This time properly. Yeah, so if it's an identity vector field, basically what it outputs is same as what it inputs. If it, let's start with 1, 0. It outputs I cap. Where is 1, 0? Here. So at 1, 0, it will be in this direction. Right. And if you look at 0, 1, 0, 1, which is here, it will be at j cap. So here, this direction. If you see it at 1, 1, we'll get I plus j. This direction. Yep. I don't know why I messed. This was too easy. Oh, I messed up, I think, for 1, 2 or something. Okay, let's do it. So if it's 1, 2, we get I plus 2j. How does that look? I plus 2j, which means it will be inclined towards the x-axis, right? Sorry, y-axis. So oh wait, that is where I went wrong. 1, 2 is not here, it is here. Yeah, so I understood. So 2, 1 will be like this. Yeah, so this is where I went wrong. Huh. Okay. This is exactly how the graph looks like. Let's try it again. X. See, beautiful. Also, technically, the length of this vector should be the magnitude of the vector outputted, but it can be scaled down because, see, if the scale is 1, it'll be a mess, whichever be the y or x. It's going to be a mess if it is going to be a mess if we don't scale the vector down. It'll be like this. We won't be able to make out anything. So for convenience, we scale down the vector to some reasonable size to analyze. So how did you guys feel? Did I make sense, or was I blabbering shit?
No, I think you made good sense, and also the session was pretty good. Yeah.